Alrighty. So I don't know if you've ever thought about this one, or if you've ever tried this, like how long of a straw can you make? I have definitely tried this, where you just take straws and you stick a straw in another straw, right? You have to kind of like bend it in. But how long of a straw can you make? And there is actually a physical limit to how long that straw can be before you can't get any, drink up the straw. So the reason that you can even drink from a straw, I thought there's a better picture here. The reason that you can drink from a straw is because the straw goes down into your drink. And when you suck on the end of the straw, it removes gas molecules that are in the straw. And that creates negative pressure. Well, negative pressure is negative relative to the atmospheric pressure. So there's less pressure now inside the straw. The atmosphere is pushing down on everything. And so it is actually pushing the soda down and up the straw to fill in that pressure that you removed. Right. I think the most ready way that you feel atmospheric pressure is when you drive up into the mountains and your ears pop, right? Or the air gets thinner. It's because there's actually less gas because there's less pressure. And we're just sort of used to that atmospheric pressure all the time. So if the straw gets too tall, at some point, there won't be enough atmospheric pressure outside of the straw to push the liquid up any farther. So there's a physical limit. And once you hit that, then using a vacuum, by sucking on the straw, you can't draw the liquid up any farther. So this is why actually in really deep wells for groundwater, they have to put the pump at the bottom most of the time, because that way you can pump the water up from the bottom instead of sucking it up from the top, because that only works up to 10 meters or so. So pressure is the first sort of property of gas that we're going to talk about. And it's really, if you think about it at a molecular level, pressure is being bombarded by atoms and molecules. So the atoms and molecules on the inside of that straw are bouncing around, and they're impacting all of the walls fast enough to cause a noticeable force. When you blow up a balloon, you're adding more atoms and molecules into the balloon, and it's those atoms and molecules that are colliding with the sides of the balloon that cause it to expand. So pressure is a force, and it's a force exerted per unit area by gas molecules as they collide with surfaces. So for car tires, we talk about in pounds per square inch, or PSI. So that's in your car tire, which is usually about 30 PSI. There's 30 pounds of force on every square inch. And atmospheric pressure, so this is the pressure of the air just above us and around us, is 14.7 pounds per square inch. So if we have a straw and a glass of orange soda, and then there's equal pressure inside and outside, right, without sucking on the straw, then nothing happens. As soon as you struck on the straw, you reduce the pressure on the inside, and then the atmospheric pressure, as I mentioned, pushes up against that, or into that vacuum. So even if you have a perfect vacuum, you can only get your orange soda up 10 meters before it just won't go any higher. This also puts a physical limit on how tall trees can be. Or actually, take that back. That's capillary action. But there's a limit to how tall trees can be based on how high they can get water up to the top of the tree. So here, if we had even a vacuum pump on our perfect straw, the orange soda would only get 10 meters. And that's because, if you imagine a giant straw that's 1 square inch, you could draw 14.7 pounds of soda up into the straw, because that's the amount of force that can be exerted by the atmosphere. All right, and then this is going to be our theoretical framework for how to think about all this stuff. And I'm going to try and come back to this a lot and talk about everything in the context of kinetic molecular theory. Because if you can understand the theory, if you can understand the why of what we're doing, then it's less about memorization, and it's more about understanding how something works, and therefore figuring out each step in a process, which maybe can sound more difficult, but it's really a lot easier, because then you can continue to apply the theory to different areas, even if it seems like it's a different question. So kinetic molecular theory is a model for understanding behavior of gases. This model predicts the correct behavior for most gases under many conditions. They're like super weird. I mean, there's exceptions everywhere, but for the vast majority of conditions, kinetic molecular theory applies very well and predicts these properties. And we're only going to talk about those conditions where it works really well. If you take Chem 1, then you'll talk more about, actually, I'll be teaching Chem 1 in the spring, but you talk more about these conditions where it doesn't work well. All right, so these are the sort of tenets of kinetic molecular theory. The first one being that gases are a collection of particles in constant motion. So even though we can't see them, the air around us is a collection of particles in constant motion. So they're flying around in straight lines. Those particles that make up the gas have no attractions or repulsions between particles. Collisions are like billiard ball collisions, or like super bouncy balls. Right? So they bounce off, they don't lose any energy when they collide, and then they bounce off sort of at perfect right angles without slowing down. The third one is that there's a lot of space between the particles compared to the size of the particles themselves. That kind of helps with the idea that there's no attractions or repulsions. They never really get close enough that they, or stay close enough together ever that they can have attractions or repulsions. And then the fourth one is the speed of the particles increases with increasing temperature. So we are currently sitting, or I'm standing in a sort of bath of particles. They're pretty spaced out, which is why we can move around pretty freely. They're all traveling in straight lines, zipping around, bouncing off of everything. If it was warmer in here, those particles on average would be moving faster. So as we increase temperature, the particles are actually moving faster because they have more energy. All right, so we're going to use these four things and use those all together to explain all of these properties of gases. So we've talked about some properties of gases before, just sort of briefly and in general terms. But kinetic molecular theory is consistent with this idea that gases are compressible. Right? So gases have lots of space between all the atoms and molecules. So you can reduce that space, you can squish them together. Unlike a liquid, where the atoms and molecules are already bumped up against each other, there's no room between them. So if you try to compress it, they really don't compress at all. Another one is the gases assume the shape of their container. Remember, the particles are all free flying around. If the door is open, there are particles flying out the door, and there will be particles flying in the door. If I, opened up a stink bomb and threw it on the ground, those gas particles from the stink bomb would spread and they would fill the room. And if the door was open, they would also go out the door. So because they're traveling in straight lines, because they're not attracted to anything, because they're flying around at random, gases fill their containers. They don't just like settle into one corner. Another property is that gases have low density in comparison with liquids and solids. So if you think about, again, lots of space in between all the particles, means that there are a lot fewer particles in a given area than there would be for a solid or liquid. So they're generally much, much less dense. In fact, 1 can of soda, if you took all of the soda, orange soda again, and you turned that into orange soda gas, you would be able to fill 1,700 cans of soda with that gas. So the volume often is orders of magnitude larger between a liquid and a gas. Again, because there's so much empty space. So if we think about pressure then, I've kind of been talking about like this already. Pressure, though, from this idea of kinetic molecular theory, that pressure, or the force, is the result of constant collisions between the particles and the surfaces around them. So they're constantly bouncing off of the walls and then going over to the other side and bouncing off the other side of the walls. And that happens so fast and so frequently that it creates like a noticeable force. And if you've ever taken, there are a lot of great YouTube videos where they'll take a tube and they put just saran wrap over one side. Then they draw the vacuum into the whole tube. They put a ping pong ball on the other end with another piece of saran wrap on the other side. And when they poke a hole in this, the force is so great that you can get that ping pong ball going supersonic speeds before it gets to the other side. And that's just the force of the gases hitting the back of the ping pong ball, rushing in to fill the vacuum. To bring it up to sort of a macro scale, imagine there was like 1,000 junior hires with Nerf guns, and they were all shooting you at the same time. So lots and lots and lots of small impacts. So as we mentioned already, pressure is exerted by gas and is defined as the force per unit area. So instead of talking about what's the force on the entire inside of this jar, we talk about for every square inch or Newton meters. I don't remember how the atmosphere is defined. Should look up those units. But we talk about just for a small area on this, what is the force on that small area? And then you could figure out, right, if you knew the whole surface area of the inside of the jar, you could figure out what the total force is. So there's a lot of things that'll change this pressure. If you've ever seen a dry ice bomb, that's an example of pressure. Breaking a 2-liter bottle, never do it in a glass bottle. In fact, at our Halloween party, we had a jar of punch, and I got dry ice. You can buy dry ice at like Winco or Save Mart. And we had a glass jar and with punch in it. And I told my wife, I said, make sure you do not put the lid out because I don't want anybody to accidentally put the lid on the jar and create a bomb. Because in a plastic bottle, it's one thing. It's loud, but generally the plastic is not going to create shrapnel. If you do it in a glass jar, now you've got glass shrapnel, and that will do a lot of damage. So never make a dry ice bomb in a glass jar. So a couple things that change whether or not there's pressure or how much pressure will be in a jar. We talked about one, if we increase the temperature, the particles are moving faster, so every one of those collisions has more energy. Or between these two, right, lower pressure, there are fewer particles inside the jar. So if there are more particles in the jar, that's more collisions. More collisions means higher pressure. And again, the most common thing is either riding on an airplane or if you drive up into the mountains, right? Changing your elevation changes the pressure difference between your inner ear and your outer ear, and that can cause pain, or it can just make it harder to hear. So when you go up to higher altitudes, then there's a lower pressure on the outside of your eardrum and a higher pressure on the inside, so it bulges outwards. And then as you're coming back down the mountain, if it's equilibrated, Then there's a lower pressure inside your ear and a higher pressure outside as you go down. Oh, good, they have them here. So the simplest unit of pressure and the SI unit, or actually I think the SI unit is the Pascal, kilopascal. The unit we're going to use the most is the atmosphere. The atmosphere is literally the pressure, atmospheric pressure on Earth at sea level, which it does vary a little bit, but we've defined it as, defined it based on the Pascal as 101,325 pascals. And then 1 Pascal is a force of 1 Newton per meter squared. So pascals are, it's really a pretty small amount of force, but it's because it's over a huge area. So instead of pounds per square inch, PSI is pounds per square inch. Oops. This is the one we're probably most familiar with. Right, that's the amount of force in pounds on a square inch. 1 Newton is probably a similar amount of force. I don't know what the conversion is between newtons and pounds, but a square meter is much, much larger than a square inch. Actually, how long is this? This is 2 meters. So if you made a square out of that, that would be 2 meters squared. Right, so yeah, the atmosphere is what we're going to mostly use. You will need to know how to convert between these, at least atmospheres and pascals. Another unit that's been used historically, because it's a convenient way to measure atmospheric pressure, is millimeters of mercury. So for millimeters of mercury, and we actually have these in the lab, they have a glass tube that's open on the bottom end there, but they fill it completely with mercury, and then they stick the end in a bath of mercury. And when you turn it over, the mercury drops, but it drops to the point where it's a perfect vacuum, and the rest of the mercury is held up by the atmospheric pressure. So if you were to take this mercury barometer and go up into the mountains with it, that mercury level would drop a little bit. And then as you came back down, it would go back up because the atmospheric pressure is changing. So this is one of the historic ways of measuring atmospheric pressure. And so a height of 760 millimeters of mercury, so that's measured from the surface of the mercury at the bottom to the top of the mercury in the tube, is 760 millimeters. That's atmospheric pressure at sea level, or 1 atmosphere. So definitely check that out in the lab. Of course, we try not to use mercury for as many things anymore because it's toxic. You can also do this, they have this water on here. Well, one of the other ones that you can do for this is also inches of mercury. So instead of measuring the height in millimeters, again, a historic thing, you can measure it in inches. And then to convert from inches of mercury to millimeters of mercury, you just convert from inches to millimeters, because it's literally just the height of the tube, or height of the mercury in the tube. So there's a table in your book, 11.1, where it has all of these different units, and then to convert between any of them, right, we can just set up relationships like this. So all of these units on this table are all equal. They're all representing the same amount of pressure, just using different units. And so these are the conversions that you should remember, because they're the most common. And they're not too hard to remember. One of them, right, so 1 atmosphere is 760 millimeters of mercury. 760 millimeters of mercury is also 760 torr. So it's the same unit, just with a different name. It is millimeters of mercury. I don't know why there are two separate names. My guess is that it comes from a different language, not English. So if we want to convert from atmospheres to torr, this will work out just like any unit conversion that we've done before. We just have new conversions. So if we start with 1.25 atmospheres, what's the relationship between atmospheres and torr? Atmospheres and torr are not, millimeters of mercury and torr are the same.
Well, wouldn't it be if there's 1.25 atmospheres and they represent the same amount of pressure, just using a different unit, wouldn't it just be 1.25 torr?
Oh, I see what you're saying. Not. So that works for just between torr and millimeters of mercury. So those ones are 1-to-1 exactly the same.
Oh,
Yeah. But it's kind of like we talked about, like the Pascal is a Newton, 1 Newton per meter squared. So it's talking about a square meter, how much force is on that. And then like PSI is pounds per square inch. So it's kind of like, in some ways, it's using different scales. Yeah. So then for atmospheres, we can write out the conversion here. So 1 atmosphere equals 760 torr. So we say 1 atmosphere, 760 torr. So then the units cancel out. Never have my calculator. So 760 times 1.25 equals 950 torr. And then for inches of mercury to millimeters of mercury, we can actually just use the conversion from, well, inches to millimeters is, I'll do it like this. Because 1 inch, or it's, yeah, 1 inch is 2.54 centimeters, but then 1 centimeter is 10 millimeters. So 30.15 times 2.54 times 10. So this is going to be 66 millimeters of mercury. So because millimeters of mercury, inches of mercury are just the height of the column of mercury, it's still just a length. So it's a little bit unique. So we want to convert 173 inches of mercury into pounds per square inch. We can find what atmospheric is for both of these. So inches of mercury is 29.92. PSI, pounds per square inch, is 14.7. And both of those numbers are representing the atmospheric pressure at sea level. So we can say 14.7 psi is equal to 29.92 inches of mercury. And which unit goes on the bottom? So inches of mercury on the bottom, 14.7 psi on top, because then we get these units canceling out, inches of mercury. So 173 times 14.7 divided by 29.92. It's going to be 85.0 psi. It's about, wow, for wider road bike tires, that's about the pressure. Some road bikes will have tire pressures of up to 120 psi, which is crazy high for a bike tire. So they're just units, just more unit conversions, more unit analysis. All right. So we're going to talk about a bunch of these named laws. In general, I don't expect you to remember the name, but I do expect you to remember the relationship that the named sort of law represents. And so I think there's 4 of these that we're going to go through, and then we'll combine them all together. So the first one is Boyle's law, and these also kind of parallel sort of like the discoveries of chemists in determining the properties of gases. So for a gas, the pressure of the gas sample depends in part on its volume. So if the temperature and the amount of gas are constant, and those are going to be 2 things that we're going to see a lot, the pressure of a gas sample increases for a decrease in volume, and it decreases for an increase in volume. So this is kind of like a bike pump. So let's put a handle on it. Right, if you have a bike pump, or if you've pumped up like inner tubes or like floaty tubes, as you're pushing down on that handle, you're decreasing the volume inside of that pump. And as that decreases, if there's nowhere for the air to go, right, you probably held your finger on the end of it and you push down on the thing, you can feel that pressure increase. So you're forcing all of these gas particles into a smaller space, and now ideally, it's plugged into your tube or whatever you're trying to fill up, and so that pressure forces it all into whatever you're trying to fill up. And that's why eventually, if you're pumping it up, if you're pumping up a bike tire, you can get the pressure inside the tire higher than the pressure outside the tire, which is what makes it work. The opposite is true then if you have this and you pull up on it and you have your thumb on top of the thing, it creates a vacuum. So the pressure inside of the pump decreases as you increase the volume. And so part of what's happening is there's only a set number of particles in this space. And so when you crush them into a smaller space, now it takes them less time to travel from one side of the pump to the other. So you get more collisions. Again, kinetic molecular theory. More collisions means higher pressure. If you take that same space and you make it larger now, it takes longer for the particles to go from one side to the other. So you have fewer collisions and lower pressure. So
how do you get the pressure in there though? Like, you know how when you pump down, you like released it into the pump, but when you bring it back down, how is there more in there? Like, you keep doing it and it keeps going in there.
yeah. So there's usually 2 one-way valves. And so as you pull up on it, one one-way valve opens from the outside and draws air in, but then the one-way valve that goes into your inner tube will seal. And so as you pull in, it's drawing air. So there'll be like a flap here, and there'll be like another flap there, and then that's like, let me draw it smaller. So when you go in like this, then this guy will open up, and air can come in from the outside, and then as you pump down again, then the air goes this way, but it can't go out the other one. So there's two valves. That's like the simplest way to do that. So as our volume decreases, so volume down, then pressure has to go up. If volume goes up, then pressure has to go down. And this is assuming that the temperature stays constant and the amount of gas stays constant. Because if you've ever filled up a lot of bike tires or a lot of inner tubes, and you've been pumping on that pump for a while, you might have noticed if you touch the side of it or you touch the hose, it's hot. And we'll get to that. Partly, a small amount of friction, but partly from compressing the gases. So this is an inverse relationship. So as one goes up, the other one goes down. So pressure and volume have an inverse relationship. See, I didn't even need to draw a ball. There's the one-way valve too. So on the upstroke, the volume increases, it causes a decrease in pressure, and then the little one-way valve in here lets in air from outside. And then as you push down, you increase the pressure and force it out the other one-way valve. So this relationship was discovered by, as it's named, by Robert Boyle. And we're assuming a constant temperature and a constant number of gas particles. So the other way to write this out is this inverse, or volume is proportional to 1 over the pressure. And then the Boyle's law equation, or what you could otherwise call the relation between pressure and volume. Right, Boyle's law is shorter. It's the relationship between pressure and volume. So using Boyle's law, we can say, if we know what the pressure and the volume is at the beginning, we can make a change to either the pressure or the volume and predict what the new pressure or volume is going to be. So this is a manometer. So you can use this to measure differences in pressure. As the pressure decreases on one side, the mercury will move, or if it increases, it'll move the other way. And so the way they did this experiment was with a manometer like this and slowly changed the volume, or slowly changed the pressure. They probably changed the volume. So here's our volume. As the volume decreases, pressure increases. And so this relationship is what V equals, well, not T, P. Right, the relationship between V and P is this, but if we take that P and instead write it as 1 over P, it becomes a perfectly straight line. Yeah.
So when you're referring to volume, it's basically size,
Yes.
right?
Yeah, volume is the space inside of your container.
So like on that J, is it because causing the pressure buildup on that chart?
Yeah, it is, but this is not the exact same experiment here, because this is 400 liters. Yeah, but that is the idea here, is that as you add mercury to the top, then it decreases the volume on the left side. Yeah, you could also use this inside of two ways to do the same experiment. So you're measuring the height here, and that's the difference in pressure. Yeah. And so this is a cool way to find relationships in math. Sometimes you can just try stuff. But if you take these graphs, it's like, okay, it's a curve, it's whatever, not a very obvious relationship. Straight lines usually denote very, very direct relationships between values. So for volume and pressure here, it's volume versus 1 over the pressure that gives you a straight line when you graph it. So again, in terms of kinetic molecular theory, if the volume decreases, but you still have the same number of particles inside of that space, same number of gas particles, then there are going to be more collisions with the walls of the container, leading to an increase in pressure. Simply because the distance from one side to the other is smaller. All right, so putting this into practice, our Boyle's law, P1 V1 equals P2 V2. So a cylinder equipped with a movable piston has an applied pressure of 3 atmospheres and a volume of 5 liters. What is the volume of the cylinder if the pressure is increased to 2 atmospheres? We've kind of gotten away from writing down givens and what we're trying to find, but this, in these gas law problems, it helps a lot. So a lot of this will come down to identifying what type of units are given. So here we've got atmospheres, which is a unit of pressure. So we'll say, okay, that's a pressure. And then we've also got units of liters. So that one's going to be a volume. And then we're given another unit here, atmospheres again, which is another unit of pressure. Yeah, let me write this, pressure. And then we need to figure out which of these is going to be P1 or V1, because we're going to get more of these. This is with fixed temperature and fixed number of moles, or fixed amount of gas. So we're going to have all of these 4 different units that are possible. So we're going to have P1, V1, P2, V2. Which of these is going to be P1? 3.0. And then our V1 will be 5.0 liters. Right, so those are sort of here together, right? 3.0 atmospheres and a volume of 5.0 liters. Those are sort of linked together in the sentence. And so that'll make 2.0 atmospheres, or P2. And then the question also asks, right, what is the volume of the cylinder if the pressure is decreased? So we're going to be looking for volume. So for P1, V1 equals P2, V2, we're going to have 3.0 atmospheres times 5.0 liters equals 2.0 atmospheres times V2. Now, based on kinetic molecular theory, the stuff we talked about with gas laws already, do you expect the volume to be larger or smaller after changing the pressure from 3 atmospheres to 2 atmospheres? Should be larger, right? So our pressure went down, so the volume goes up. Opposite, inverse relationship. So this will be, and yeah. You're going to multiply first, and then I'm going to keep, until we cancel out units, we keep all the units in there. So this is going to be 15.0 atmosphere liters, because it's atmospheres times liters. And they got 2.0 atmospheres times V2. So we divide both sides by the 2.0 atmospheres. So then, right, those will cancel, and then our atmospheres will cancel, and that'll leave us with 7.5 liters equals V2. So being able to keep those units in there is a really powerful thing, which is part of unit analysis, but it gets a little bit more complicated here. But it's a really powerful thing for determining the answers for gas law problems. Because we're going to have 4 different possible units. So one of the keys for Boyle's law and any of these other simpler gas laws that we're going to talk about is making sure that you have the units the same on both sides of the equation. So we couldn't use atmospheres and then use torr or millimeters of mercury over here. And they both have to be in atmospheres so that these units will cancel. All right. What makes gas laws hard is having so many different equations. So Boyle's law also explains for divers why ascending too quickly is dangerous. Because for every 10 meters of depth, a diver experiences an extra 1 atmosphere of pressure. And so there's a air pressure regulator on their tank, because as they go down, their air pressure coming out of the tank needs to match the pressure in the water around them. Because as you're going down, there's more water pressure pushing in on your entire body, but in this case specifically your chest cavity. And so if the pressure coming in from the tank doesn't match the pressure outside, you won't be able to take a breath. This is why if you've ever tried to take a pool noodle and go down underwater in a swimming pool and try to breathe through the pool noodle from the bottom, it's really hard because your lungs are fighting the pressure from the pool pushing on you, around you. And then it's just, of course, amplified. You're not diving. I mean, it'd be cool if you had a 10-meter deep pool, but it would be also wild. So unless these pressures are equalized, you won't be able to breathe even if you've got a full oxygen tank. So then, of course, we could do problems related to things like this. So if a snorkeler takes a syringe filled with 16 milliliters of air from the surface, where the pressure is 1 atmosphere, to an unknown depth, the volume of the air in the syringe at this depth is 7.5 milliliters. So first question is, what is the pressure at this depth? If the pressure increases by an additional 1 atmosphere for every 10 meters of depth, how deep is the snorkeler? So there's a lot here. So let's identify first. Here we got 16 milliliters. Milliliters is a unit of volume. And then we have atmospheres, which that one is pressure. And then milliliters again. And then we also have another pressure and a distance, or in this case specifically depth. We are in the Boyle's law section. It's the only thing we've learned so far. So let's start with Boyle's law. So P1, V1 equals P2, V2. And I think part of the tricky thing about a word problem like this, which I might give you a word problem like this, but I'll probably break it up into like A and B parts, right? So this, what is the pressure at this depth? That would be A. And then B would be, the second question is how deep is the snorkeler? And give you this information there.
Does it matter if the B goes before the P? When you're doing calculations?
It doesn't, no. Yeah. So the trick here though is, whoops, P1, V1, P2, V2. Which of these units should we use in Boyle's law? Well, we've got three different pressures. Or actually, I guess we've got 2 volumes and 2 pressures, but is this pressure actually related to Boyle's law? Because what we're trying to find is what is the pressure at this depth?
Okay, so it's like let's pretend we don't have that yet then, right?
Right, exactly. Yeah, so this part, the second part here is don't worry about this section yet. You don't want to plug that 1 atmosphere in. So we're starting at the surface, right from the surface, so 1 atmosphere. And then 16 milliliters. And then our volume 2 is 7.5. And again, you can take a second to think, okay, does that make sense? You're diving underwater, the pressure increases, the syringe gets smaller, so that makes sense. And so as our pressure should be increasing then. So if we take these and we say, okay, 1 atmosphere to start, 16 milliliters, and then move that so it lines up. Then pressure is what we're looking for, times 7.5 milliliters. And again, for these simple gas laws, the volume, the units just have to be the same. That won't always be the case. So we're going to get 16 atmosphere milliliters equals P2 times 7.5. All right, and then divide both sides by and I just want to, again, highlight this, how the units cancel and work out to giving us the units that we want. So 16 divided by 7.5, 2.1, I guess it's just 2.1 atmospheres equals P2. So 2.1 atmospheres is the depth, or is the pressure where the diver is now. So now how deep did the diver go?
10 meters, and if it increases for 1 ATM for 10 meters,
Mm-hmm.
wouldn't it be the 2.1 times 10?
Uh,
Is how you could figure out how much
yeah,
the atmosphere increased.
pretty much, yeah. And we could set this up a little more formally to say, right, for every 10 meters, that's 1 atmosphere. So if we're starting at the surface of 1 atmosphere, going down, we've only increased the pressure by 1.1 atmospheres. Well, so because we started at 1 and we only went up by 1.1, So we increased by 1.1 atmospheres. Then we multiplied that increase in the change in atmospheric pressure, or the change in pressure, then by this 10. So we went 11 meters. So the atmospheres cancel out. Because if you had gone down 20 meters, then the pressure would have increased by 2 atmospheres, so we'd be at 3 atmospheres. So it's this, if the pressure increases by an additional 1 atmosphere.
So we don't even use the 2.1.
We do, yeah, well, so we started at, it's 2.1 minus 1.0 atmosphere that we started at equals 1.1 atmospheres. So instead of just taking the pressure at that depth, we have to take the pressure at the depth, or we have to take the pressure at that depth and subtract the starting pressure because it's how much the pressure increased.
See, when it said increase by additional, or in my mind, it would be add 2.1 plus 1,
Well, how much pressure did we add?
additional 1.
So we started from 1, and how much did we add to get to 2.1? 1.1. Yeah. That one's tricky. That one's tricky. You could get most of the points if you had multiplied 2.1 by 10. All right. Yeah, that one's a trickier problem and requires some thinking outside the box a little bit instead of following the formulas. All right, so the second law that we're going to talk about, probably the one we're going to end on today, is Charles' law. It's the relationship between volume and temperature. So we did pressure and volume, now we're doing volume and temperature. So why does hot air rise? If you heat up air, it takes up more space. But because the number of gas particles is the same, there's just more space between them, it becomes less dense. All right, so mass doesn't change, so the density increases. So if this V gets larger, and this is one of those ones too where, like, take some numbers, plug them in here, and prove it to yourself. If our mass is 10, and we have a volume of 10, right, that equals 1. If our mass is 10 and our volume is 100, that's 0.1. All right, so as the volume gets bigger, if the mass stays the same, density gets smaller. And we don't often think of air like this, but it's the reason that hot air balloons float is the same reason that wood floats in water. It's less dense. And so what happens is the water ends up just sort of pushing it out. That's more physics though, buoyancy. So for hot air balloons, you increase the temperature of the gas and the volume increases. So here you have the volume increases with temperature. And you can actually, if you do this calculation, you can extrapolate the line all the way back to negative 273 degrees C. And at that point, volume will equal about 0. And so since we can't get negative volume, negative 273 degrees C is absolute 0. So you can't get any colder than that. Even space actually isn't that cold. It's very close. It's about 2 degrees above absolute 0. So Charles discovered this relationship between volume and temperature, and where our volume and pressure were inversely related, right? If volume goes up, the pressure goes down. Volume goes down, the pressure goes up. Volume and temperature are directly related. So if you increase the volume, you have to increase the temperature. I guess I should talk about it because it's easier to change the temperature. So if you increase the volume, this is the one that always throws me off, because if you force the volume to increase, the temperature is going to decrease. But if you increase the temperature, the volume increases. If you decrease the temperature, the volume decreases. So these are directly proportional. And I think one of the confusing parts is we write it out a direct proportionality as V, and this means proportional to T. But the equation is V1 over T1 equals V2 over T2. This is when you can actually do at home. If you have a balloon, you can blow up that balloon and then stick it in the freezer. And then when you pull the balloon out later, it will be smaller. It'll be all kind of shriveled up and sad. But if you let it warm up, it'll go back to its original size. And then if you had a way of heating it, you could heat it. If you heat up water and then stick the balloon in the hot water, then the balloon will get larger. Hot water. So if you want to put it in hot water, because if you just like hold it over the stove or something, it'll probably pop. So you have to heat it gently. So that's why I say heat it. Use hot water to heat it. And the key here is that you have to use the Kelvin temperature. So these are the first required units. You have to use Kelvin. Kelvin is the absolute scale of temperature. 0 Kelvin is absolute zero. Because when the temperature of a gas sample in kelvins is doubled, its volume doubles. But that's only in Kelvin. So if you go from 100 Kelvin to 200 Kelvin, it'll double the volume. But if you're in degrees Celsius, it's not going to work out. Actually, let's go back into this. There's a couple weird things that can happen. So if we have a volume, let's say we have a volume of 1 liter, and we have a temperature of 10 degrees Celsius. The problem is that doubling 10 degrees Celsius only means going up to 20 degrees Celsius. But in kelvins, this is 283.15 Kelvin, and that's only going up to 293.15 Kelvin, which is not doubling, right? So when you convert everything over to Kelvin, these become much smaller changes. The other thing that can happen if you're using Celsius is you can have 0 degrees Celsius. So what is 1 divided by 0 degrees Celsius? Undefined, infinite, it doesn't work. So for these, make sure you're always using Kelvin. And it's very likely that I'll put a question on there that makes you divide by 0 degrees C if you don't convert it to Kelvin. Sometimes some people still push on. They write undefined, or whatever the calculator says. So remember, these have to be in Kelvin. And this is because we can use this equation of the line where B is the y-intercept. And by using Kelvin as a temperature scale, that makes our y-intercept 0, which makes everything simpler. Otherwise, you've got to do other transformations. The kinetic molecular theory behind this, though, is that if the temperature of a gas sample is increased, you are increasing the energy of all of the gas particles, because that's what temperature is. It's the kinetic energy of all the particles in the air. And as those gas particles move faster, for our pressure to remain constant, the volume must increase. That's why if you take a balloon, and if you were to heat up all the air in that balloon, they start colliding with the sides of the balloon more, and that will force the balloon to get larger to maintain the same pressure. Or if you take it and you put it in ice water, you decrease all of the energy for those particles. So now they're not moving as fast, and they're not colliding with the sides of the balloon as often. So the balloon shrinks because there's not enough pressure from the particles on the inside And those particles on the inside are competing with the particles on the outside. So it's kind of like a tug of war. So if they have the same energy, the balloon stays the same size. If the inside has more energy, then the balloon expands until it matches the particles on the outside. Oh, perfect. Look at that. So again, identifying between these, right now we're doing them in order. This, says Charles' law, so we're going to use Charles' law. But on any other question, how would you know to use Charles' law or Boyle's law at this point? And yeah, I was going to say, I'll actually ask that question now. How would you know? So you know to use Charles' law because temperature is involved. And pressure is not involved. So if we look at our units, we have 2.8 liters, and now 2.8 liters at an unknown temperature. When the sample is submerged in ice water at 0 degrees C, its volume decreases to 2.57 liters. So what was its initial temperature in Kelvin and in Celsius? Right, so we only have temperatures and volumes. Because we can say this is a volume, this is a temperature, that's a temperature, and that's a volume. So that's going to be Charles' law, or the relationship between temperature and volume. So we're going to have V1 over T1 equals V2 over T2. Okay, so what is our V1 and T1? 2.80 liters for V1, but our temperature is unknown. And that's going to have to be in Kelvin, at least as we're solving the problem. And then our second volume is 2.57 liters. And our second temperature is 0 degrees C. So to convert that into Kelvin, it'll be 0 degrees C plus 273.15. So that's going to be 273.15 Kelvin. And then plug and chug. Oh, but this actually does present a perfect opportunity. So this equation can be used this way with volume on top and temperature on the bottom, or you can flip it upside down. So it could also be, and this is the same thing, T1 over V1 equals T2 over V2. And the reason you would want to do that is if you're solving for temperature, you want temperature to be on top because it makes it a little bit easier to solve for. If you're solving for volume, you want volume on top because it's a little bit easier. So here we're solving for T1. So we'll flip this. And we can say T1 over our volume 1, which is 2.80 liters. And then T2 is 273.15 Kelvin, has to be in Kelvin. And then our volume, 2.57 liters. So if I zoom on this, all right, so then we multiply both sides by 2.80 liters to move that to the other side. So this will cancel with that. And then again, the units work out here. Liters will cancel with liters. So we can do 273.15 times 2.8 divided by 2.57. So T1 was 297.6. Actually, that's too many sig figs. It's just 298 Kelvin.
How did you do that on the calculator?
You could do either way here. So you could do 273.15 divided by 2.57 and then multiply by 2.8. The order for multiplication and division doesn't actually matter.
Okay. So you would do 273.15 divided by 2.57 multiplied by 2.8?
That would work, yeah. Hmm, 34 of 69. Okay, yeah. Oh, yeah, if we wanted to find this in Celsius too. So to go from Celsius to Kelvin, we add 273.15. So to go back, we'll say 298. So 298, and you should really use the whole number, minus 273.15. So it's 24.4 degrees C. Yeah. All right, and that's what we'll leave off for today.